Okay, welcome back. Today what we're going to do is we're going to talk about um, kinematics, motion, in two dimensions, starting with what we would get if acceleration were constant. And the first thing we notice, if we set stuff up like this, we know that we can treat motion along any one coordinate axis as if it's independent from what's going on along another coordinate axis. So this means like we can break up position vectors into having an x component and a y component, a velocity vector into having an x component and a y component, an acceleration vector into having an x component and a y component. So we could have some overall acceleration with some components that are, for instance, related to the size of the total acceleration times the appropriate trig functions related to their angles for the appropriate components. So we had our acceleration vector was off in some direction, some angle theta a away from the x-axis. You could break that down into different components. You could relate it to the you could relate those components to the overall acceleration through Pythagorean theorem, like we could with any other vector. And we can do the same sort of thing with original velocity and final velocity, original position, final position, and so on, with those having their own different angles that are associated with those particular vectors as well. And so because we can break down the overall acceleration and velocity and position into component vectors that are aligned with the coordinate axes, we can then look at how they all relate to each other, how all the components of those quantities of motion relate to each other. So we have, when we were working in one dimension, we didn't specify necessarily whether that was some x direction, some y direction, or what those even mean, up, down, left, right, forward, backward, north, south. So here we've got motion along an x-axis, and we're looking at it's related to its velocities and accelerations through the components. The original x velocity times time plus 1/2 the x component of the acceleration times time squared, and so on through our other equations of motion. And we get a similar set of equations that go along with motion for what goes on in the y dimension. If we want to up this to 3D, we'd have to have another set of equations for the components that go along in the z direction as well. And then our triangles become more complicated because we have to throw in another triangle and another angle that relate the xy plane to the z plane. We're not going to do that in this video, or in the classes that I teach generally. But let's see what we've got going on here. So we have all these, and we can connect these together. And in the high school courses that I teach, we often don't play with these in more of the general case like we have here. We look at a more special case for what goes on for two-dimensional motion, where we look at what I'm going to call ideal projectile motion. So let me erase this here, and we're going to transition to ideal projectile motion. And we're going to do that. We need to understand what this term means. In general, let me see this first. In general, when we talk about projectile motion, we mean that the only force that's non-negligible, the only significant force, the only force that matters as far as how precise your predictions are is gravity. So we say gravity is the only non-negligible force. So we're going to make that assumption. Doesn't mean that other forces don't exist, but that we don't care about them enough in our model. That we think that our model of projectile motion is such that those forces are so small, we can run the equations as if they're not there, and we'll get close enough to reality with what we've got. You could pretend that it's like you're operating in, say, a vacuum, but no air resistance, no air drag, that sort of thing, no lift. Other forces that could exist for things flying through the air might be thrust if you've got engines. I'm not worried about electricity and magnetism, but those are things there. Now, in your introductory physics courses, we get even more elementary. That is, we make assumptions to make the model even simpler than that. One thing we're going to do is we're going to assume, that the range, the horizontal range, is very small compared to the radius of the Earth. But why that matters, if we have that being true, then the difference between having a flat Earth and a curved Earth is negligible. This makes it so that gravity points the same direction all flight. Or also, because with the real world, if you have, the Earth, and you're here on one part of the Earth, maybe you're like me, and you're on the east coast of the USA, and you've got gravity, pointing down towards the center of the Earth this way. Gravity still points down when you're over in the South Indian Ocean, off the coast of Southwest Australia, on the antipodes from New England here. But acceleration down, is this way for me, and it's that way for the folks on the antipodes, or antipodes, however you're supposed to pronounce that. But with a flat Earth, Or with an Earth that's flat enough and the range is small enough we can't tell that the Earth is flat, or is it flat? Then they all point, then down is the same, down is parallel all over the full flight. We're also going to assume that the maximum height, that the vertical range, is also a lot smaller than the radius of the Earth. And that's going to make it so that, or it's going to help make it so that gravity is constant with height. And so these together are going to tell us this. These together are going to tell us that acceleration in the y direction is negative g, where g is our 9.80665 meters per second squared. I'm making down be positive, or down be negative rather. So negative g is negative 9.8 meters per second squared, negative 32 feet per second squared. And we get to have those going on. We also, and so I can go ahead and I can substitute that in here. All my AYs I can swap in with negative g gravity being the only non-negligible force makes it so that AX is 0. So that makes this term disappear. This goes to 0 and so does this. And so if we look at what's going on in the x direction, in the horizontal direction, we see that there's no change in velocity. And if there's no change in velocity, we don't have to differentiate from final component in the x direction for velocity and original component for the x direction and velocity. They can all be the same. And this equation here is redundant. It tells us no new information than the one above. Both basically tell us that the velocity is constant in the x direction. The x component's constant. And so we're reduced essentially to one equation of motion for our components in the x direction. But we have all of these. We have like two independent equations of motion in the y direction. I've thrown a third there. There's another one we can derive as well that's also dependent upon any two of these others. But that's what we've got going on here. There's another assumption we can throw in here if we like, or that we can make note of if we like. We can assume that the time of flight is very small compared to Earth's rotation, 4 hours. And that effect means that we don't have to worry about the Coriolis effect. No negligible Coriolis effect. That is, over long distances, compared to the speed of the object, because the Earth is rotating, objects are going to tend to veer off to the side. And I'll have to do another video that will go into the details for why that happens after we get into forces and inertia, when it will be more relevant. But this is it. This is what we're starting with. So these are our assumptions. These are the equations we get to play with. But like I specified with the general case, we get to connect these to each other. We see from what's here, we can connect them because the time is going to be the same whether it's in the horizontal direction or the vertical direction, where we did not explicitly state that, but we've been working with that idea here that this is horizontal and this is vertical. So that's how we connect horizontal motion to vertical motion, is through time. There's another way that they connect, and that's the way that we alluded to earlier. Your position vector, let's say let's make this final position, theta r has some x final, y final component. Maybe you've got some v final, with vx and vy final, theta v final. And then our acceleration is just going to be down, so I'm not going to bother putting that triangle up there. We get another velocity triangle for original velocity, get another position triangle for original position. But that's how these all get to be connected to each other through the angles and the components. We get to build up the overall positions, the overall velocities for some given point in time. So that's our groundwork. This is our setup. These are our equations we get to play with. I will come back in a moment after I reorganize these into something more compact, and then we'll work through a couple of practice questions.